Hello everyone, once again you are welcome to class. The topic before us today that we are going to discuss is sound spectrum. The introduction. Have you ever imagined why sound becomes louder when you approach its source or when the source approaches you? And also why sound faints when you move away from the source or when the source recedes? This happens as a result of variation in the frequency of sound waves. Remember, we had earlier examined the characteristics of sound waves. In this particular video, we will describe sound spectrum and its frequency. This will help you to understand why you are able to detect or hear some sound, why some sound waves are inaudible. The learning outcomes. By the end of this lesson, you will be able to, number 1, explain sound spectrum, 2, classify sound spectrum into frequency regions, 3, differentiate between each of the frequency regions, and lastly, solve simple numerical examples on frequency spectrum. Now, when we talk about sound spectrum, what do we mean in particular? Sound spectrum is a graph or a chart that displays frequency regions of sound waves. Similar to electromagnetic radiation, sound waves also have different frequencies and form a spectrum. It has two axes, the vertical axis that represents the loudness or the amplitude of that sound, while the horizontal axis represents the frequency. I want to talk about the figure beside the text that I have here. Now we have two figures there. The first one is displaying the variation of pressure with time. The second one displays the variation of amplitude with time. Remember, amplitude has to do with the maximum displacement of that sound wave from its equilibrium position. Now when you look at the first graph on top there, you see that the pressure varies in a jagged form with the time. But when you look at the second one, the frequency axis there is order of 1000, that is kilowatts. Now you can see there are some sharp points in the amplitude while the amplitude diminishes with the frequency. As the frequency increases, the amplitude diminishes there. Now, when we talk about the frequency regions, what do we mean by that? Sound spectrum has relatively few frequencies, and we can classify or divide them into 3 frequency regions. The first one, we call it infrasonic. Now, when we talk of infrasonic frequency region, we are talking to sound frequency regions whose frequency are greater than 20 Hz. The second one is audible or audio frequency range. This one has a frequency between 20 Hz and 20 kHz. That is, its frequency falls in the region between 20 Hz and 20,000 Hz. And lastly, the third one is the ultrasonic frequency. Ultrasonic waves, they have frequencies greater than 20,000 Hz. So these three, infrasonic, audible, and ultrasonic, they are the ones we classify as frequency regions of sound spectrum. Now I want to talk about the audible region. For humans, the audible region is about 20 Hz to 20 kHz. We can hear sound due to vibrations of our eardrums caused by sound waves. We get our sense of hearing from the cochlea, that is the tiny fluid organ in the inner ear, which provides our sense of hearing and our sense of balance. Now when you look at the figure beside the frequency regions here, we have ultrasonic at the upper part, we have audible at the lower part. Now we have said earlier that frequency greater than 20 kHz, we call them ultrasonic, while for audible, frequency range between 20 Hz and 20 kHz. Now anyone that is greater than 20 kHz, we call them ultrasonic frequency range. Now sound waves with frequencies greater than 20,000, like I said earlier, they are referred to as ultrasonics. Now they cannot be detected by the human ear. The human ear does not have the ability to detect this sound, although some animals like dogs, bats, and so on, they can detect this sound wave. Ultrasonic reflection has found applications in so many areas like seismic surveying, for example in geophysical prospecting, maybe for oil or for water in a particular location where water is scarce. Then in the location of cracks in metals. It has also helped in industry to locate cracks or defects in metals or welded joints. Likewise, ultrasound to form images of the internal organs of fetuses in pregnant women, and automatic focus cameras. Bats also use the reflection of ultrasound for navigation and to locate food. Now the figure I have beside me here shows application of ultrasonics in particular in the use of ultrasound to view the images of the fetus or maybe the womb or the uterus in pregnant women. That is what that diagram is displaying. Some regions are dark, some regions are a little bit brighter. Now, using a probe in the hospital, the nurse or maybe the radiographer will be able to view everything that is inside that pregnant woman's womb, or if there is no pregnancy there, they will be able to view the womb clearly. Now I have about two numerical problems here to solve in form of a sound wave. Now the first one is saying that what is the wavelength of a sound wave in here with a frequency of 22 megahertz. Now mega has to do with 1 million, so we first convert that mega to ordinary hertz. So we multiply that 22 by 1 million, that gives us 22 million hertz. And like we know the formula for calculating the wavelength of sound waves, the wavelength will be velocity divided by the frequency. So we divide 344 by 22 million, and that one gives us 1.56 times 10 raised to power minus 5 meters. For the second case, the question reads, for ultrasonic examination of unborn babies, a frequency of 2 megahertz is used. If the speed of sound in the uterus, that is the womb, is 1500 meters per second, what is the wavelength of these waves? So similarly, like the way we did for example 1, we'll do the same thing for example 2. Wavelength is the velocity divided by the frequency. But the frequency in this case is 2 megahertz. So we convert it to hertz by multiplying it by 1 million. That gives us 2 million. Then going by our formula, the wavelength will be 1500 divided by 2 million, and that comes out to be 7.5 times 10 raised to power minus 4 meters. So for the first case, the wavelength was 1.56 times 10 raised to power minus 5 meter, while for the second case, the wavelength is 7.5 times 10 raised to power minus 4 meters. In the next presentation, I will be discussing echo and reverberation with you. Thank you for listening, and God bless you.